What's up, class? Welcome back to our lecture series, Miss Cose's Pregnancy Series. We are going to be continuing our study of the senses, and today we're going to be talking about our ears, our hearing sense. But before we begin, I would like to introduce you once again to my very handsome husband, Landon Cose. Woohoo! You're my favorite.
Thanks, baby. You're mine too.
Yeah. Okay. Thanks for letting me reset that up. All right. So today we're going to go through our hearing sense. And then the next one that we'll do is our vision, which I'm really excited about because it's our last one that we'll be covering of the five senses. So the only one we didn't really cover is smell, but smell is highly related to tasting. And we kind of covered it during the respiratory system. So I think we're good. So let's just start out. What is your favorite song or musical artist? So you can pause the video, go around, get everybody's opinion, see if people have good music taste or not. But Landon, what is your favorite song or musical artist?
Favorite song?
And talk like pretty loud.
I think that's a tough one. I think one of my favorite songs ever is Stairway to Heaven. I think it's like a perfect song. And favorite artist? I'd probably put Led Zeppelin up there too.
Okay, let's go.
Yeah.
Are those both rock? That might be a dumb question.
Yeah, Led Zeppelin is rock, and they
Okay.
did Stairway to Heaven.
Okay, yeah. Landon loves rock music. I know he's in a good mood when he's playing rock in the car. But I wanted to shout out my husband actually because I think he's a musical savant, specifically in making and curating playlists. So when Landon when we first got to know each other, Landon made me this playlist called Year One, and it was our first year of knowing each other. And he put all these like really cool songs on it, and it kind of like romanced me in a lot of ways. So I want to encourage the men in here, if you're good at making playlists, you can make them for the girl that you're interested in, and it will work wonders. But he's made a playlist for every year since we've been together, which is kind of cool. Now we're on year 4, and he's in the process of making that playlist now. So I want to share this with you guys. And if you didn't already know, you can actually choose an image for like your playlist, which is kind of cool. It doesn't need to be like a mix of the albums. So like the second one was like a letter that I had sent Landon in the mail when we were doing long distance, and I had like drawn this like lion on it. So that's kind of cool. But we're talking about music because today obviously we're talking about your hearing sense and how that works. Everyone is gonna have with them a notes worksheet handout from the sub today from our professor in class. So make sure you have that. If you don't, pause the video, make sure everyone has one. It'll have the image of this on it, and we'll be labeling that throughout the lecture. And then there's actually gonna be one more image right below it. So let's start out just with the anatomy of the ear. What are the different parts of our ear? So the first part that we're gonna talk about is just like what we would call our ear, which is like this outer piece. This is what we call the auricle, or another name for it is the pinna. They're synonymous. But what the auricle does is it funnels sound waves into the inner structures of the ear. So this actually has a purpose in the same way that a funnel is shaped to get certain liquids or solids into like a bowl or a space. Our ear acts the same exact way. And it's actually oriented, if you notice, it's oriented forwards. So that's why when someone says something behind us, we naturally turn around in order to hear their sound waves better. So that's why this picture is here. Someone's like talking to someone in front of them. But what happens is that these sound waves are traveling all throughout the air around us, and our auricle, our ear, will funnel those sound waves so then we can process them. The next part of our anatomy of the ear is going a little bit deeper in, and it's called the external auditory canal. External auditory canal. I put these blue lines in to demarcate the entire space on your image here. And what the external auditory canal is it's just directing all those sound waves that have been funneled in, and it's directing them toward the tympanic membrane, which we'll talk about. But what this space also is for is, this is kind of what we would think is our inner ear, but it's actually technically called the outer ear. This is the space that we shove like Q-tips into our ear, and they're always like, don't, you're laughing? Yeah, Lane and I both do that. And everyone's always like, don't do it because you're shoving more wax deeper into your ear, and then it'll actually like butt up against the tympanic membrane or your eardrum and get stuck and affect your hearing. But if we're all honest, we all do it anyway. But another thing is, I want to bring this up, is what happens if a bug gets into your ear? If a bug gets into your ear, do you guys think that it can make its way all the way to the brain? I don't know. Go ahead and answer the question. What do you think, baby?
I think with enough persistence and determination, anything can.
That's true. The bug technically could get through the ear, but it'd have to like eat through a lot of bone and membranes to actually get there. In reality, if you get a bug in your ear, it's going to be stopped by your eardrum and it'll be held in this external auditory canal. So I have a question for you. Do you know what to do if you do get a bug in your ear, like a spider or a moth or a fly, and it's not coming out? What do you do?
I've seen videos of them put like a certain type of like caustic like liquid in the ear, and then like pushes out and they grab it.
Oh, like it like pisses off the bug?
Yeah.
Dang, that's crazy. Like alcohol or something?
I'm not sure the actual solution, but whatever it does, it causes it to like come out.
Okay, that's scary. I read like this in a book one time, so I put this in here, but I read that you can lay your head, like have the bugged ear up, and you pour olive, baby, or mineral oil into that ear, and essentially it will suffocate the bug, and so the bug will naturally try to find air, and so it will come out of your ear either dead, like it drowned, or it will find its way out and you can grab it. So if this ever happens to you, you know what to do. This is like an at-home remedy. All right, now we finally get to that elusive tympanic membrane that we've been talking about. Our tympanic membrane is right here, and this is what we call our eardrum. We call it that because it actually turns those sound waves, because sound is a wave, turns sound waves into a physical vibration. And those vibrations are going to be carried on to a different part of our ear. But this tympanic membrane is actually the dividing line between the space that we call our outer ear, so that's the external auditory canal and the auricle, and then the middle ear, which is just this section right here. Because of this separation that happens, this means these two cavities are separate from each other. This is why when we get on an airplane, we go up into the sky, we feel pressure build in our ear. And that's because there's a pressure difference between the outer ear, the external auditory canal, and the atmosphere here, and the pressure within the middle ear. So if there's a difference here, it can cause pain, irritation, and you want to rectify that, which we've talked about before. But what's cool about the way that the tympanic membrane moves is as a sound wave comes, it's going to vibrate and will actually preserve the frequency and intensity of that sound wave. That's why we can hear pitches, differences in volume, because the tympanic membrane preserves that. So I have a question for you. We were talking about the airplane and kind of getting the different pressures between our outer and middle ear. What allows our ear to equalize that pressure? We've talked about it before when we went through the respiratory pathway. What do you think, Landon?
It's the tube connecting like the middle ear to the kind of not your nasal cavity, but just like oral cavity.
Yeah. Do you remember what it's called? I think it is nasal cavity.
It's not the eustachian tube.
Yes, eustachian tube is correct. The eustachian tube. So here we can see this small tube on this diagram. The eustachian tube isn't permanently open. It opens as we move our jaw, so it kind of like closes and opens like this. That's why chewing gum is helpful on an airplane to equalize the pressure. But you already said this. Where does the other end of the eustachian tube lead to? It leads to the oral nasal cavity. So we see that it actually is nasal. I shouldn't have put oral here. The nasal cavity. And we saw that when we labeled our respiratory pathway. All right. Now we're finally getting into the middle ear. So we're out of the outer, now we're into the middle. The main thing the middle ear has is 3 auditory ossicles, or 3 ear bones. Have you heard anything special about the ear bones? The ear bones are the
smallest bones in the body.
The smallest bones in the body, that's true. And there's 3 of them. They're called the malleus, which is the outermost one, the incus, which is the middle one, and the stapes, which is the last one that actually comes in contact with parts of the inner ear. They also call them these other names because they're shaped like this, so malleus, hammer, incus, anvil, and stapes, stirrup, but we'll use the technical names today. What these do is they amplify the vibration that's coming from the tympanic membrane, and they do that because we're going from a large surface area to a small surface area in the stapes. So that actually increases the power of the vibration. That's important because when we get to the inner ear, the vibration isn't going to be moving through air anymore. It's going to be moving through fluid. So that's why we need to amplify the vibration itself. So to start out, we have the malleus, which is also called the hammer. It's attached directly to the tympanic membrane and it receives those vibrations from the sound waves. Next, we have the incus, which is the anvil, and it sits between the malleus and the stapes. So it's just a middle bone, just the middle, and that transfers those vibrations. You guys don't need to write this down all the way. I would just want you to have them labeled because they're kind of intuitive if you have them labeled. You don't need to write this word for word, and you'll have the slides if you want them. And then lastly, this is, I think, kind of the most important one, is the stapes, which looks like a stirrup. And this one sits directly on the oval window of this bony labyrinth that we're going to talk about. That's the inner ear. And what it does is it pushes the vibrations into the fluid of the cochlea, which we're going to talk about. So you can check this out right here. We have the tympanic membrane flexing in and out from all these sound waves coming in. And we can see all the bones working together to translate those sound waves into vibrations. And finally, the stapes is pushing against this structure of the inner ear that we're about to talk about. So finally, we reach the inner ear. The first part of the inner ear we're going to talk about is called the vestibule. And that's this middle section of this entire like snail-like looking structure. It's called the vestibule. And you see that that's where the stapes actually comes in contact with the vestibule, is in a space that we call the oval window. So there's not like a demarcated spot on our labeling image. So you may just want to like draw a little circle around where the stapes comes in contact with the vestibule, and then that will be your oval window. And like we said, the oval window will convert the physical vibration into fluid waves that will then go into this kind of snail shell space, which we'll talk about. But to the left and upwards of the vestibule, which is the middle of the snail, is what we call the semicircular canals. And these are really cool. Semicircular canals have 3 of them, and they're on the 3 different planes of the XYZ axis. So if we're just in math class, can you see this on the video?
I just checked it.
Perfect. If I know that we have left space on this side. Say we're in math class and we're like graphing like slopes and stuff, right? We have like the XY axis, and then sometimes we even add an axis that's like coming at us. Sometimes we do it like this. So it's like we have an XYZ axis. So it's on all 3 planes. So we're dealing with something 3-dimensional. That's what's actually happening with these semicircular canals. So we have a semicircular canal on the X, Y, and then the Z axis. So this allows us to detect 3D space. So what it does, like it says up here, is it detects the angular movement of our head for balance and rotation. So that's why sometimes when we throw our head or something, like you get kind of off balance. That's because the fluid within these semicircular canals of your ear is moving, and it gets caught up, or certain things can happen that cause a lack of balance. So you can actually see how we detect the orientation of our head by these semicircular canals from these GIFs. So you see a person going up and down with your head, you see the fluid going forward and backwards in this axis of one of the semicircular canals. Then you see the same thing with going side to side, and then you can get the picture of, okay, I see if I'm tilting my head this way, the fluid is going to move this amount within each of those canals, so it orients us in space. Now, what is it called when someone is very disoriented and dizzy? Do you guys know what they call it? Oh, I have
vertigo.
Vertigo. I have vertigo. And people will talk about me like, I didn't know which way was up or down. I was so disoriented. I couldn't even walk. I couldn't go to work. So vertigo actually has to do with something going wrong with these semicircular canals. Do you know what it is, Landon? What's going on? It's okay if you don't. I know that this isn't very important in your medical field.
I mean, I guess sometimes they can get not stuck, but like...
Yeah,
it's almost like input overload, maybe.
Yes, totally. Okay, so what's actually happening is we actually have calcium crystals inside of our inner ear. So inside of this snail-like guy. And they're actually supposed to be in the vestibule, which is the middle part of the snail. We're supposed to have these calcium crystals. And that vestibule, it does a lot more things than just connect the two. I'm trying to simplify here for our class. But sometimes those crystals can dislodge. There's a ton of reasons why. It could be from a trauma, like a car accident. It can be from old age. It can be from a virus or an illness that we go through, and it can dislodge these crystals from the vestibule, and they'll make their way up to the semicircular canals. When they do, the crystals are heavier than the fluid that's moving. So you'll move your head and the fluid will move like normal. And then after the fluid stops, the crystal will still be moving. And that's what completely throws your entire system off balance, because now it's not having the proper input that it's supposed to. The crystal is disrupting it. So that's what causes vertigo. So super interesting. A malady within the semicircular canals by having those crystals get in there. So then there's some things you can do to reset them. Like, I know there's like a lot of osteopathic stuff. One of my friends had this one time, and this guy did some stuff with the ear and had them do certain things with their head.
Epley maneuver.
What is it called?
The Epley maneuver.
Epley maneuver?
Yeah, so that's for benign paroxysmal positional vertigo.
Okay.
So yeah. So
what do you do for that? Or how, do you know?
Well, you can check it by like leaning the person back with their head to the side, and you'll see their eye start going side to side. It's
okay.
called astigmatism.
Oh,
so it's like a diagnosis, and you can tell what side it's on. And then I don't remember the maneuvers like in order, but you're kind of just like having them literally move around.
To get the crystal back or whatever.
Yeah, it's literally like reorienting that.
That's crazy. That's really cool. So this is how vertigo works. All right. Finally, we get to the most exciting part of the inner ear, and I think the entire ear in general. And that's almost this, like, I always think of like Gary the snail from SpongeBob. And it's like, it kind of looks like his shell, but it's called the cochlea, or like a conch shell. It's like similar to that shape. And the whole job of the cochlea is for hearing. So like the semicircular canals were for balance and orientation, cochlea is simply about hearing. And what the cochlea does is it converts the sound waves that were then turned into fluid waves. So this should say like fluid waves or stationary waves into a neural signal. So actually something that your brain can then be sent. And the way it does that is through something called the organ of Corti, which actually is just a series of membranes and hair fibers, which we'll talk about. Because what is in this cochlea is like this giant long series of hair fibers, and those fluid waves will come across and bend hair fibers at a certain point. That'll send an electrical signal to your brain saying, oh, hey, it's this volume and pitch. So we're going to explain how this works. So let's take our little cochlea right here, and we're going to unwind it all the way out. I'm unwinding it. So now we have it completely flat. We would never see it in the body like this unless you're like dead, something bad happened, but it'll help our understanding. So in this front part, there's like a kind of canal or tube system, and we call it the scala vestibule. That's on the top. This is exactly where those fluid waves are going to be coming in, is right through here. So they're going to be coming in. And you kind of see that they're going to come through this top section. Oh, this is supposed to be a GIF, but I guess it didn't work. But essentially, they're going to come through this top section, and they're going to disrupt this middle membrane, this middle cavity called the scala media. And it'll actually push down the scala media, the waves will. And then the wave will come all the way around to the bottom, which is the scala tympani. But mainly, we're just going to be focusing on the scala vestibule and the scala media, which this middle part is also called the cochlear duct. So you guys can label these on your page right now because you actually have this in the bottom. And so what's really cool about this is I think we said this, the fluid waves or standing waves will travel down the scala vestibule, like we said. So they're traveling down, and they're going to push down into the hairs that are in this scala media. So this entire middle section has all these hairs that are facing up like this. And wherever they push down a certain hair will determine the pitch of that sound. So we know like a higher pitch is like I think, and low pitch is like a guy like, oh. So a higher pitch is going to push down the hairs closer to the beginning, the proximal side of this cochlea. So will push down right here, a high frequency sound, and like oh will push down far away. And so this is how our brain will figure out what pitch a certain sound is at, is by doing this. Then I want to show you how it's like converting that into an electrical impulse. So what we're going to do is we're just going to chop part of this entire section off and open it up, almost like I'm chopping a long straw and I'm showing you the inside. So I'm showing you the inside of this right here. So here we have the scala vestibuli. This would be this top tube. In the middle, the scala media. That's this middle tube that has the hairs that we know about. And on the bottom here is the scala tympani. That's the bottom purple. So inside the scala media, the middle part with the hairs, is where we find the organ of Corti. And earlier we said the organ of Corti is what turns those fluid waves into an electrical impulse that goes to the brain. So what the organ of Corti has is this entire unit right here. And it has three main things in it. It has one, a tectorial membrane. And as the sound waves are coming down this scala vestibuli this way, or across this way, the waves are going to come down and push on this tectorial membrane in the middle part. And as it pushes down, it's going to come in contact with these little hairs that are coming up. I'm going to zoom in for you so you can see it better in a second. But when the hairs then get bent, the hairs are also called stereocilia. Stereo like a stereo in your car. Stereocilia, the little sound hairs. The sound hair then depolarizes when it gets pushed down. So it sends an electrical signal down a nerve, which then is going to turn into the greater nerve, the vestibulocochlear nerve, see it's cranial nerve 2, which we'll talk about. So let's just zoom in a little bit so we can understand this better. So we have that fluid wave coming down. When the fluid wave comes down, it presses down on this tectorial membrane, which now we've zoomed into. And look, now we can see the stereocilia, those little hairs that are up in this space right here. So as the tectorial membrane comes down, it pushes and it bends the hairs down. And you can see here, there's actually 5 hairs on each of these little hair cells. And the reason why is each of them get shorter and shorter. What do you think this will help us determine? Why do they get shorter as they go? Kind of see that.
It's maybe more the amplitude.
The volume, yeah, the amplitude or volume of something. So if just one of the hairs gets bent, then we're like, oh, it's a softer sound because the wave has less amplitude. But if all 5 hairs get bent over by the tympanic membrane, that's a way louder sound. So it's going to be a different type of signal that ends up going to the nerve. So once any hair is bent, it'll depolarize the cell. And we know depolarization leads to an action potential. So an action potential will then travel down the nerve. So then that information can then go to the brain, to the auditory center. So, like we said, it's going to go down these nerves from all these different hairs that are getting pushed down and go to this greater nerve, which is cranial nerve 7. Oh yeah, cranial nerve 7. 2 is optic. I said 2 earlier. Or 8, sorry.
Yeah, it's
cranial
eight.
nerve 8.
Yeah.
Cranial nerve 8 is called the vestibulocochlear nerve. How did we get this word?
Well, you have the cochlea and the vestibule, and you have the
Yes.
vestibular, like, proprioception. And
Yeah. So we have the 2 parts of the inner ear that we just talked about, the vestibule, so vestibulo, and the cochlear, which is that snail shell part that we just unwound. So we're just putting those 2 words together to make the nerve. So once that signal gets sent, it goes down that cranial nerve 8, and then it gets sent to the auditory cortex in the brain. So name that lobe. Name that lobe. What lobe of the brain has the auditory cortex?
Temporal lobe.
Temporal lobe is correct. See, Landon should have been at our Jeopardy. He would have loved it. Temporal lobe is where we have the auditory cortex. So finally, this is a lot. You don't need to write it down. But I just wanted to review all the things that we have learned. So let's start from the sound wave outside of our body and bring it all the way back in as a final review. Our pathway of sound is when a sound wave enters through the outer ear, through the auricle, and then comes up on the tympanic membrane. When it hits the tympanic membrane, it vibrates and it creates that physical vibration. The physical vibration will pass through the 3 ossicles. We have the malleus, the incus, and then the stapes. Once it goes through those, the stapes, the last one, will push on the oval window of the vestibule, of that inner ear system. Then, this pushing on the oval window will create fluid waves in the cochlea, in that snail shell shaped type thing, which will move the scala, that top part of it. And it will bend the hairs, also known as stereocilia, in the organ of Corti. Then when the hair cells generate a nerve signal by depolarizing, the signal will travel on the vestibular cochlear nerve, CN8, and then that will head to the auditory cortex in the temporal lobe. So that is how we hear things. That's how it works. I hope you really enjoyed this lecture, and I hope you guys enjoy your interactive lab today. See you next time.